This is section 2.1, and we start with a story problem here. Very simple one, actually. You are driving down the interstate when you notice you are at mile marker number 100 at 1 p.m. 2 hours later, you notice you are at mile marker number 220. What was your average velocity or average rate of change for those 2 hours of the trip? Well, anytime I've talked about average velocity or average rate of change in a car, we're talking about miles per hour. And so really it says we've gone for 2 hours, so we already know that this is going to be over 2 hours. We just have to know how far we went. Well, if we started clocking this at mile marker 100 and we stopped at mile marker 220, we've gone 120 miles. So you simply divide and you find out that the average velocity was 60 miles per hour. Now if we look at the next question, it says, how fast were you going at 1:34 p.m., which would be roughly a half hour after you start clocking this. Well, unless you were sitting and staring at the speedometer and mark it at 1:34, you don't know how fast you're going given that the information in this paragraph above. And that's a lot of what calculus is about, is finding what we call instantaneous velocity. In our next slide, we're going to talk about average and instantaneous speed. A moving body's average speed during an interval of time is found by dividing the distance covered by the elapsed time. That's what we just did. The unit of measure in length per unit time, kilometers per hour, feet per second, or whatever is appropriate to the problem at hand. In example 1, we want to find an average speed. A rock breaks loose from the top of a tall cliff. What is its average speed during the first 2 seconds of fall? Solution. Experiments show that a dense solid object dropped from rest to fall freely near the surface of the earth will fall y equals 16t squared, and this is going to be I believe feet, so we're looking at feet per second. So if we plug in the end of the 2 seconds, 16 times 2 squared minus 16 times 0 squared, that's going to be the distance that the rock, are we looking at a rock here? Yeah, a rock breaks loose. That's how far it falls. Over, divided by 2 seconds. So we have feet and then per second. So we have 16 times 4 over 2, which is 64 over 2, which ends up being 32 feet per second. And that's the average velocity. But if we want to know how fast the rock was falling, let's say at 1.3 seconds, we're going to need to know a little bit more than average velocity, because that's instantaneous velocity once you talk about how fast something is going at an instant in time. In this slide, we're going to find the instantaneous velocity of the rock at 2 seconds. Well, what we looked at before was the average velocity over the 2 seconds. We never looked at how fast something was going at an instant in time, called instantaneous velocity. But let's talk about what we did before to find average and see if we can relate that to instantaneous velocity. Well, to find average velocity from 0 to 2 seconds, we looked at the 2 points really when we plugged values in for y. And what we did was we plugged 2 in for t, and we got 16 times 2 squared. And then we plugged 0, this is the point actually, 0, 0. We plugged 0 in for t and got, really what you do is 16 times 0 squared. I know that's going to be 0 in the end. And then you divide by 2 minus 0. Well, remember, these are function values, both of these, which are y values. This is actually y2, and this is y1, and this is x2, and this is x1. So really we have y2 minus y1 over x2 minus x1. That should be instantly recognizable if you've gotten this far in math as the equation for slope. And so when you find the average rate of change, what you're really doing is finding the slope of that secant line. Well, we want to find the average or the instantaneous velocity at this one point, but we don't know how to do that with 1 point. We can only find slope with 2 points. We need a minimum of 2 points to find a slope. So what if we brought this point in closer to the one that we're really looking at? This would start to get closer to the actual slope at that point, which is called a tangent line. So this is actually the tangent line, but we have to use secant lines to approximate the slope of this tangent line. The tangent line, if we could get it exactly, would be instantaneous, and all the slopes of these secant lines is just an average rate of change. Well, we're actually going to use average rate of change to find instantaneous rate of change. And we're just going to start bringing these 2 points closer and closer and closer until they practically touch. In other words, the difference between their 2 points, the difference in the distance between the 2 points is nothing. It's 0. And that involves limits. So we have the limit as, and the distance that between these 2 points, we're going to actually call this point x, and I know it's 2 right now. We'll talk about that later. And we're going to talk about a very tiny increment just after that, and we're going to call that x plus a little bit more, and we assign that the letter h. So now we're going to bring this distance to 0 until these 2 points are going to be right on top of each other. So yeah, we're using 2 points, but if they're going to be on top of each other, that's going to be the instantaneous rate of change. So we have the limit as h approaches 0. We want to get these 2 points to be right on top of each other, so we really have a tangent line rather than a secant line. And so we want y2, we want the second y value, so we have f of x plus h, and then we want to minus the y value for the x, so we have minus f of x, and then we're going to divide that by the x2, x plus h, and then minus the x1, which in this case is just x. And we're going to turn all these into 2's in a little bit here. So we have the limit as h approaches 0 of 16 times, now this isn't just an arbitrary x value, in this case it's actually 2, so we have of 2 plus h squared minus 16 times 2 squared, and then that's all going to be all over 2 plus h minus 2. Well, now we just do some algebra with this. We have the limit as h approaches 0 of 16 times 4 plus 4h plus h squared, and then minus, let's see, 4 times 16, that's 64, and the 2's are going to cancel out on the bottom, and that just leaves h. So we have the limit as h approaches 0 of 64 plus 64h plus 16h squared minus 64, and that's all going to be over h. All over h, and that's limit as h approaches 0 of, well, the 64's are going to cancel out, and you can see both of these have an h, so we can divide all by h. So we have 64 plus 16h, and of course the denominator is gone now because we divided everybody by h, and now we can finally plug 0 in, and we end up with 64 feet per second. So the instantaneous rate of change is 64 feet per second, and we use that with the concept of secant lines to find the slope of the tangent line. And you can do that as long as you know the equation for how the position is changing. In this next slide, we are asked to do pretty much the same thing, so let's get to it here. We have a free fall. A water balloon dropped from a window high above the ground falls. Y equals 4.9 t squared meters. In t seconds, find the balloon's, first of all, A, average speed during the first 3 seconds of fall. This is just the slope of the secant line. So in letter A, it's going to be f of first, how many? 3 seconds. F of 3 minus f of 0 over 3 minus 0. So we have really 4.9 times 9 minus 0, of course, because we're starting at 0, over 3 minus 0. So I can really cancel those out. Those minus zeros aren't going to matter. I can divide 9 by 3. So what I really need is 4.9 times 3. Let's see, 7, 2, 12, 14.7 meters per second. In letter B, this is a little different. We need the speed at the instant t is 3. So now at 3 seconds, we're looking for the slope of that tangent line, not the slope of secant lines, but we're kind of using the slope of secant lines to get to the tangent line. And we're going to take the limit as the difference between the 2 points approaches nothing, approaches 0. So we have 4.9 times 3 plus h minus 4.9. Oh, that's squared. 4.9 times 3. Whoops, actually, yeah, 3 squared. All over h. So that's going to be, let's see, 4.9 times 9 plus 6h plus h squared minus, I need the 4.9 times 9, and that's 44.1. I forgot my little limit statement here. I'm going to have to squeeze it in. And that's all over h. Equals limit as h approaches 0 of 44.1 plus, let's see, 6 times 4.9, 29.4h plus 4.9h squared, and then minus 44.1, and then that is all over h. You're going to see something similar happen that did before. 44.1s are going to cancel, and then everybody's divisible by h. So we end up with the limit as h approaches 0 of 29.4 plus 4.9h. And if you plug 0 in for the h, you get 29.4, and that's going to be meters per second. Let's look at limits with infinity out of section 2.2. We have the equation 3x minus 2 over x plus 2 times x minus 3 with the limit as x approaches infinity. What we end up having with this is we have really 3x over x squared, and that's the part that really is going to matter as x gets very, very large. Imagine taking 3 billion minus 2. The minus 2 really isn't going to affect the problem very much, and when we expand this out, we have x squared minus x minus 6, and this part really isn't going to matter much anyway. So we're really looking at taking the limit as x approaches infinity of really just 3 over x when the numbers get extremely large. Now when the x values are small, that's certainly going to make a big difference, but when they're large, it doesn't hardly matter at all. So imagine if the x was very large, 3 over 4 billion. That's going to be very, very small number. So this is approaching 0 as x goes to infinity, and it approaches 0 as x goes to negative infinity as well. Now the same concept applies here. These don't really affect the function for very large values of x. So we're just looking at 4x squared over 2x squared, the limit as x approaches infinity. These x squareds can cancel out, and the limit is actually 2. So when the powers are the same, you just use the coefficients. If the power is bigger on the bottom, it's an automatic 0. And then if the power is bigger on top, then we're looking at no horizontal asymptotes at all. So this isn't leveling out, it's actually going off to infinity. So we have no horizontal asymptotes, and the limit doesn't exist either. There's no limit. We are asked to use the sandwich theorem to find the limit as x approaches infinity of sine of x over x. Well, think about the biggest, let's look at the smallest value sine can be. We have the limit as x approaches infinity of negative 1 over x, because negative 1 is the smallest sine can be. Now it's going to be less than or equal to the limit as x approaches infinity of sine of x over x, and the biggest sine can be is a value of 1. So we have the limit as x approaches infinity of 1 over x. So we've squeezed our problem in between the smallest and the biggest value sine can be, but both of these are 0. So 0 is less than or equal to the limit as x approaches infinity of sine of x over x, and that's less than or equal to 0. So we've squeezed this in between two zeros, so that means this must be 0. Here's our last example, and we're going to find, here's the function, 4 over x plus 2, 8x to the third minus 4 over 2x to the third. We're going to find the limit as x approaches infinity of this function. We're going to take it one little piece at a time. So we have the limit as x approaches infinity of the 4 over x plus the limit as x approaches infinity of just 2, and we can take that times the limit as x approaches infinity of, well, think about limit as x approaches infinity and ending behavior are really the same thing. So all we have to consider here is the x to the thirds. So we have really just 8 over 2. So this is going to be, well, let's look at this. If x gets extremely large, this is going to get extremely small. So we have 0 plus 2. The limit of any constant is just that constant, and then that's going to be times 4. So this answer is 8. And the limit as x approaches negative infinity is not going to change any of these functions, so that is also